Welcome to part 2 of Muscles 2. So last lecture I got cut off quickly as my cat was clawing at the door, I confess. We had finished here with the sarcomere reminder, and now we're going to go on talking about summation. So this is what the muscle is going to do. It's going to increase its tension over time up to a maximum tension that can be acquired by that particular muscle. So that term here, when you get to the maximum tension, but yet you still visualize some relaxation happening down, coming down like this, that term is incomplete tetanus. Some books also refer to it as unfused tetanus. Okay, so it's increasing, summating, because we're delivering these action potentials so quickly. It will summate up to a maximum tension. So remember we were talking about the sarcomeres. It has to do with the sarcomere not having time to completely relax. So if it overlaps a little and gets another action potential, it'll overlap more. Another action potential, overlap more. Another action potential, overlap more. And what you end up is with an increased tension here, which is what you want to do. So the word tetanus is very confusing to people because you think of it as a disease, lockjaw, and it's not that in human physiology. It's a whole different word. Tetanus is what a muscle achieves when it achieves maximum tension. So don't confuse physiology tetanus with the disease, is what I'm telling you on the slide here. You actually want tetanus in your muscles. You want to achieve maximum strength because when you're trying to lift something very heavy, you would like to create a lot of tension, a lot of force in that muscle. So think of it as something that you do want. You want tetanus in your muscles. It's also going to allow you to have coordinated muscle contractions and not be twitching, right? You don't want a little twitch and stop and twitch and stop. Okay, incomplete tetanus. Now, what happens if you have a single twitch and then you increase this frequency? Let me get my pen back. And you increase this frequency as is happening here, and you're going to have summation, right? Summation, and then at a certain point you're going to reach that maximum tension with no visible dips. In other words, no visible relaxation happening at all in that muscle. You want that again. You want to lift that weight and you want to be able to hold it without that muscle relaxing at all. You want to hold a contraction. Well, when we visualize it like this as a straight line up here without the up and downs up at the top, then we're going to call it complete tetanus or fused tetanus. Either of those words are synonymous. So the muscle contraction is smooth and prolonged. There's no relaxation between the twitches. Okay, big summary here. Single twitch, summation, and then if we have still little relaxation, it's going to be incomplete tetanus until it irons out flat and it'll be complete tetanus. So think of what's happening at the molecular level. What changed? The frequency at which the action potentials were delivered. We went from just deliver to going boom, 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 boom. And that fast delivery of action potentials does not allow the relaxation of that muscle and increases the force. So if you had slow delivery, you have slow force, fast delivery, increased force or increased tension. We're using those two words synonymously, force and tension. This is a diagram that isn't super clear, but it shows them separate like this. Twitch, summation, unfused tetanus because we don't see it as a straight line, and then fused tetanus when it's straight across. And if you look at the delivery, the stimulus frequency, it's very infrequent, a little more frequent, quite frequent and very, very frequent. And that's fused tetanus. So you can hold that fused tetanus for a while, and then there will be fatigue. So this is what we do in the regular semester. We have some equipment that allows you to hold on to a sensor that's measuring the force, and you can hold that, and after a while you can hold it no longer and your muscles are fatiguing. So there's a couple of different types of fatigue. One is psychological fatigue and the other is physiological fatigue. In psychological fatigue, there's warning coming from your brain telling you, oh, stop, you're done, you can't run anymore, you can't hold this anymore, this is too heavy, stop. It's trying to warn you so that you don't damage muscle, right? So it's coming from the brain, that cell is running low on nutrients, maybe on ATP, you start to feel tired and you want to stop. The actual physiological fatigue is when the muscle is biochemically unable to respond to an impulse from a motor neuron. And we can study that again in a frog leg. This is, again, a dissected frog leg that you can stimulate, and you watch that tension rise, and you watch tetanus as it contracts fully, and it stays that way. And it stays that way for a long time. And if you keep stimulating it, eventually it's going to just relax. And that means it's reached its physiological fatigue. But it takes a long time, even for a little muscle of a frog. So the causes of fatigue show, we don't fully understand it, but we do know that ATP is not the limiting factor. We seem to be able to continually manufacture enough ATP so that that's not the limiting factor. Instead, it's probably glycogen stores that are depleted. And so if we've stored some of that glycogen in order to release glucose, maybe that's part of it. Maybe that depletion is going to affect the release of calcium. So if we can't release calcium from the sarcoplasmic reticulum, then no contraction because we have no calcium. Maybe there's an increased phosphate that comes from creatine phosphate that we haven't talked about yet. That comes at the end of this chapter. It's a form of fuel that we have, creatine phosphate, that's going to easily release a phosphate for you to be able to have the power stroke happening. So that increased quantity of phosphate there probably slows the release of the power stroke. So the power stroke, when too much of this accumulates, maybe has trouble releasing, and that starts that mechanism of fatigue. Your book has a section on fatigue, a couple paragraphs, and it shows how we're still uncertain of exactly of the mechanisms. The other possibility is that those phosphates combine with calcium, making calcium phosphate inside the muscle. And then you have this accumulation of calcium phosphate, and again resulting in lower levels of calcium available for the power stroke. So ideas, they could all be happening. Some could be happening. It's probably a combination. Potassium concentrations are going to rise in the extracellular fluid also from the repeated contractions, correct? Because you're pumping out potassium and bringing in sodium. So that imbalance could be part of the story. Perhaps the sodium-potassium pump starts to malfunction once this contraction has been held for too long. Again, questions at the end of these because we're uncertain. So we have one more slide. We think a lot about DOMS, which is delayed onset muscle soreness. You know, why is it that you are sore at the end of a workout? And mostly it's tiny tears in the muscle tissue, in the fascia or in the muscle cells. Overstretching or tears in the connective tissue, so either in the muscle tissue or connective tissue, which is fascia. Maybe it has to do with fluid retention in the surrounding tissue. So there's a loss of fluid here. The membranes start to get a little leaky. Sometimes there's muscle spasms, the soreness. And inflammation, where you have white blood cells going to that area, more fluid going to that area, redness in the area. This could be happening from, overuse of a muscle or sustained contraction for a long time. Again, calcium regulation we don't fully understand, as we don't understand cramps very well, leg cramps. What is it exactly about that muscle that isn't functioning correctly? So those are some of the reasons for delayed onset muscle soreness, and we're going to stop this lecture now. Thanks.